So welcome back. We start today talking about split algorithms for L2 plus L1. This is section 3.4 from Professor Gilbert Strang textbook. Now, this is the main outline for today's lecture. I'll talk about basis pursuit and split algorithms. Maybe in the split algorithm, I'll talk about the Lagrangian and the gradient ascent algorithm. Okay? So I'll go slowly. So what is the problem? What is the problem context here? We are talking about a matrix A which has many columns. So let us consider a linear system, AX equals B, where A has many more columns than rows. Okay? So N is much larger, number of columns, much larger than M. Of course, M here is the number of conditions in the linear system of variables or entries in the X factor. So in that case, if you focus on AXN equals 0, it would have many solutions. Okay? It has what we call a large null space. While if AX equals B has one solution, then every X plus XN is another solution. Okay? So now the question is which one among all these solutions to choose. So one of the possibilities here is to choose, as we did previously in the pseudo-inverse and the least squares problem, is to choose the X plus with minimum norm that solves the problem X plus equals to A plus B. A plus here the pseudo-inverse of A. Okay, now previously what we did is just to minimize the L2 norm. And this is what we did to minimize the norm of X. We remove its null space component. Okay? In fact, that leaves the minimum norm solution, which was agreed in section 2.2, given by A plus B, and it's also one part of the one question in the exam, in the current homework running. So it came from the pseudo-inverse. But this X plus, in fact, will generally have many small components. What do you mean by small component? There are non-zero components, which can be very difficult to interpret. They are small, but they are not zeros. Okay? So in MATLAB, for example, if you use the p-inv version, which is the pseudo-inverse version of A times B, we can find easily X plus. Okay? So I'm giving you a hint just to verify, for example, the solution of one of your homework questions. Okay? Now, but I'd like you to also to work it manually. So, but if you do the backslash A over B, it also finds a fairly sparse solution. With MATLAB, I'm still talking. Here the backslash didn't appear. Probably not the optimal X for the basis pursuit. Okay? What do you mean here? We mean to generate a basis here or a vector with which is more suitable than the X plus solution. The solution to AX equals B, which fits the many zeros components condition. So we would like to have now a sparse solution if it exists. It comes in fact from the minimization of the L1 norm, the L2 norm. So this is the basis pursuit problem, where we set the minimization of the norm of x1, so the norm 1 of x, which is basically the sum of the absolute values of all the entries. Okay? So this is the norm. In general, Shabab, when we talk about the norm P of x, it's in fact the pth root of the sum of the absolute values of the entries here. Okay? So when you talk about the L2 norm, you're talking about P equals 2. Okay? When you talk about P equals 1, so the L1 norm, you're just summing up the absolute values. Okay? So in the basis pursuit problem, we minimize the L1 norm subject to AX equals B. Okay? Basically, we're looking for the X that solves our problem AX equals B, but which has a minimum L1 norm? Well, in fact, this is a convex optimization problem. Why is it convex? Anyone has an answer? See, especially the guys from system engineering, which I shouldn't be hiding now, because I can point them one by one. Firas, do you have any answer to this?
Just a second, I'm looking at it.
Okay, Abdullah, any answer? Abdullah Baroum.
Yes, not yet. I don't have an answer.
Not yet. Guys, I'm shocked, honestly. You did at least one operations research course, one linear programming course, right? Am I right?
Yes.
Okay. Can I say that any linear program is a convex optimization problem? What does convex mean here? What is a convex set? It's very simple, guys. I'm just going to plot, okay, a figure, and hopefully everyone will catch. So I'm going to draw a figure, and is this set? Okay. Convex. Is it convex? Yes or no?
No, I think.
Why? Why is that not convex? So what is the definition here? If I have 2 points here in my set, okay, can I say that any convex combination of them belongs to the set? Here, yes. But sometimes, okay, if I move my point here, the second point, let's say I'm calling it B, and moving it down towards this edge, probably, you can see that not any convex combination of A and B is in my set, okay? You got it? So this is not a convex set. While, in fact, if you take this triangle, it is a convex set. Any linear combination of any pair of points here would give you just another point in the set itself, okay? So basically, in linear programming, guys, what are you doing? You are minimizing or maximizing. It doesn't matter, okay? Linear function, right? Linear function, so we mainly call it CTX, for example, linear function, where you have linear conditions. With linear conditions, anyways, remember, for example, the dimension 2 representation of the feasible region, okay? You always end up with a convex set. We call this is always convex. That's why, in fact, this is the main thing behind the principle of the simplex algorithm. Just you are iterating on the edges of a convex set, okay? And even the anterior point method, you are traversing a convex set. Get it, guys? It's very simple. Don't be shocked with words. What you need to master is the definition, is the technical terminology, okay? Convex set is a set where if you take any pair of points in the set or elements in the set, any linear combination of them, or any convex combination of them, puts you inside the set, okay? So if I take, for example, alpha x plus 1 minus alpha y here, I'll always be in my set, okay? Which I might call S or where alpha is less than 1, of course. You will always be in your set. Okay, so let me go back to my things. So it's really trivial, guys. Main thing behind these, the linear programming, all the linear programming course is that we are working on convex sets. Okay, so we were here. Yeah. So this is a convex optimization problem. You have a linear function or quasi-linear function. Okay? Then you are working on a convex set AX equals B. Now, a related problem allows for noise in AX equals B. And in that case, you may say that an exact solution is not required. Now, there is a very important branch in statistics. Actually, I have many colleagues working basically on lasso and shrinkage. And in lasso and statistics, they kind of use a least square with penalties, as we already detailed before. So they try to minimize half of the square of the L2 norm of AX minus B plus the penalty, lambda, times the L1 norm. Okay? Or they may also set it not as a penalty, as a condition where the L1 norm of X is less than some value, usually, for example, 1. Okay? So this is a way to deal with it with the lasso in statistics. And we already talked about it briefly in section 2.2. So if we move forward, what do we need to define? Now, to solve this problem, the problem of finding the X which has the least L1 norm and which is a sparse solution, we need to set, first of all, the objective. Now, the goal is to minimize F1x plus F2x for X in a convex set K, as we said, for example, AX equals B. Well, we have two parts in the objective. First of all, the F1 involves an L1 type norm. Okay? Basically, you are minimizing the sum of the absolute values of the entries of X, for example. And the F2 norm, the F2 involves an L2 type norm optimization. In the following, we are going to define split algorithms that solve this kind of objective. In fact, split algorithms, they allow to alternate between these two objectives, the L1 type and the L2 type norms. And the split iterations, in fact, in practice, are much more effective and fast than combining L1 and L2 norm in one step. And among the leading algorithms, you may cite the ADMN, the split Bergman, and the split X-Mars algorithm. But before reaching these algorithms, we need to introduce some of the, historically, the steps or the algorithms that, in fact, were kind of prelude to these more developed algorithms. So one way to start is to study the development of the algorithms that made the final ADMN, in fact, algorithm a success. So the final goal here is to reach the ADMN part. Okay? First of all, this is a typical thing we see, the Lagrangian, okay, in basic optimization course. If you take anything about nonlinear optimization, or even sometimes included or incorporated in any linear optimization course, for example, I was giving part of it in Math405 a couple of years ago when we talked about linear and nonlinear programming. So we define what you call the Lagrangian. Okay? Here, in fact, we minimize f of x subject to ax equals b. Okay? In general, of course, the Lagrangian works for not only for linear, in fact, conditions and linear functions. Where A is a kind of matrix which is m by n. In fact, the Lagrangian introduces a set of multipliers. We call them y1, ym. You will see later on why I'm picking these variables, y1 till ym. Okay, and guess what? You have as many Lagrangian multipliers as your number of conditions, as your number of rows. Okay, so the Lagrangian function writes as L of xy. So instead of working just on minimizing f of x, you'll be working on minimizing L of xy. So what you did is bringing these ax equals b conditions into the objective, but multiplied with the yt's, okay, with the multipliers. So basically, you have a non-constrained optimization problem now. Okay? You may develop and you can write it this way, but generally it's not practical. Okay? So Basically, you are just, it's kind of adding penalties also to the objective. Now, the combined solution, which you may call X star, Y star, is in fact a saddle point of L. Okay? It's a saddle point of L. Well, there are, in fact, a set of equations to solve. First of all, if you differentiate the L, the Lagrangian, now with respect to the axis, you need to find a zero, okay? And also, if you differentiate the L with respect to the y's, you need to find the zero, okay? So the split algorithm now is, it works iteratively on taking the solutions to the L over dy equals 0, which gives back, in fact, solution, the system AX equals to B, and take the solution to the L over dy equals 0 and plug it where in the L over dx conditions. Okay? Now, after you solve the dl over dy equals 0, it comes the key step from the primal problem. We call this the primal problem. And you'll see later on why we'll have to talk about the primal problem. But those who did at least one operations research course know that when we talk about primal, it means that we are going to talk about the dual problem, which is to minimize Lx y over x. In fact, the minimum occurs where at x star and depends heavily on the y you choose. Okay? And since we talked about the primal, we are going to introduce just in the slide after the example, the dual problem, which is my L xy x star of y. Okay? So now I would like to take an example to show you how the Lagrangian. Okay? Maybe you forgot it, maybe you didn't do it before. So let's see how things work. Okay? So here I have a small minimization problem. I have 4x1 squared plus 2x1 times x2. So this is the objective. Got it, guys? Following? So subject to two linear conditions, which are 2x1 plus x2 equals 5 and x1 plus 2x2 equals 4. Is it okay? So let's first step, let's write the Lagrangian. So the Lagrangian x and y takes the same function here, same objective function, 4x1 squared plus 2x1 x2, and adds the penalties or the multiplies y1 and y2, multiplying the two conditions ax minus b, as you see. Got it? Okay. Now, if you differentiate this Lagrangian with respect to L, to this Lagrangian, sorry for that, with respect to the y's, what do we get? You get, again, as we explained, the two conditions. Yes, you get 2x1 plus x2 equals minus 5 equals 0. Am I right? So basically here, it's like saying that x2 is equal to how much? x2 is equal to 5 minus 2x1. And if you take the second derivative, first partial derivative, of course, with respect to y2, it gives you x1 plus 2x2 minus 4 equals 0. Minus 4 equals 0. So basically now you can plug this expression of x2 and you end up with 2x2 equals 4 minus x1. Am I right? Now if you plug the same x2, it's like saying that 10 minus 4 x1 equals 4 minus x1. So basically, it's like saying that 6 is equal to 3x1, so x1 is how much? x1 is 2. Okay? Got it, guys? If x1 is 2, then x2 is how much? x2 star is just 1. So we got the x2 and the x1. Okay? Now, if you want to go one step further, what do you need to do? You are going to compute you need to find the values of the y1 and the y2. Okay, so the adequate multipliers. So then you need to differentiate the L with respect to x1, which gives you how much? It gives you 8x1 plus 2x2 and plus 2y1 plus y2. Okay? So basically now this needs to be equal to 0, and you have a linear system now because of the substitution. You plug in the x stars here, and also similarly, the derivative with respect to x2 will give you 2x1 plus y1 plus 2y2. So if you plug in the x stars, you get the solution. Now I'll let you verify it. If you check here, you're going to have this item is going to be 8 times 2 plus 2, which is how much? It's 18. Okay? So you have a linear equation which involves only y1 and y2. And also here you'll have 4. And you will end up with this solution. Okay? y1 star, which is equal to minus 32 over 3, and y2 star to 10 over 3. Okay? So these are, in fact, the Lagrangian multipliers value at the minimum of this of this problem. Okay? Got it, guys? Let's figure out.
What if the constraints are an inequality type?
Okay, if the constraints are inequalities, you can either add a slack variable, Firas. Slack variable means or an accident variable, because you have two types of inequalities. Okay, either it's a less or equal or greater or equal. If it's a lesser equal, for example, you add plus s and equals, it matches your b, which means now you have added a new variable to the problem. We call it the slack variable. If it is a greater or equal condition, you just subtract the accident variable. It becomes, for example, minus s, which equals b or d. Get it? And so this is done as a pre-processing before writing the Lagrangian. Okay? So basically, you will increase the number of variables.
Okay, and then yes, I got the step.
Yes, this is the first step. You may find people willing to take the inequality itself as it is and just put it like we did here. And the condition now in the when you differentiate would not be equal to match a 0. Just to find ax, for example, was less or equal to b. Then the condition in should be ax less or equal to b. The most important idea is that the differentiation with respect to the multipliers should give you back your original system of equations.
Okay, it's good.
Okay, but in fact, in linear programming, what we do, we add the slack variables and it works fine. Okay, think of it. For us, we're still working on a convex set here. So basically, adding slack variables or accident variables resolves the equation. Now, the last thing I'd like to show you today is about, well, the work on the dual of this. Okay, so in fact, those who did operations research, in fact, before, whether taking it in the system engineering department or the math department, it doesn't make a big difference. They know that if that objective was linear, in fact, this would have been called a primal, and there is a corresponding dual. Okay, and these two problems, in fact, they are interrelated. For example, if your primal is to minimize in linear programming CTX such that AX is larger than B, I'm taking the most general way to write it, okay? Then the dual would be to maximize, okay? It maximizes BTY, okay? Such that YTA is larger than C, is less than C, okay? So the correspondence here is that with the YT is also positive. the corresponding here is that these objective coefficients become the right-hand sides of the conditions in the dual, and the same happens with the b's. If they are in the objective coefficient of the dual, they should be in the right-hand side of the primal. And the same A is here, in fact. So, in fact, the y's in linear programming here are the same as the Lagrangian multiplier in the general case. Okay, in case you are having a non-linear function to optimize. Got it? And of course, in linear programming, there is no optimality gap. It means when you optimize, in fact, the primal or the dual, you can also find the exact solution to the other problem. Okay? In fact, any reasonably good software does both at the same time. Okay? And there is an interrelation between both of them. So the last thing I would like to show you is that how to solve on the solution of that problem. So to maximize, in fact, the dual function, we look for a point y star where all the partial derivatives are zeros. So in other words, in fact, we work on the gradient of this dual to make it equal to 0. It has, in fact, a neat formula for those y derivatives. If you differentiate, in fact, again, you get ax star minus b, which is. And here, in fact, we look at it from a numerical point of view, and we define not the gradient descent, but the gradient ascent, because our objective here is to maximize them. Okay? And there are mainly two steps. First step is to increase. So we'd like to find the xk plus 1 that minimizes, of course, you start with an initial yk, okay? So for example, at step 1, you need a y0 to start, okay? So numerically, you can solve this problem here. So you find what is the argmean, you find the xk plus 1 that minimizes the L x yk. So the yk here, for example, at iteration 1, you may consider y0 and just an initial solution and find the corresponding x1. Now you take your x1 and you plug it in the gradient of L, as you see, and you just update your yk. Okay, so you write yk plus 1 is equal to yk plus sk times a times this difference between ax k plus 1 minus b. So in fact, this ax k plus 1 minus b, it maps the difference in how far are you from meeting the b's, how far are you from satisfying the conditions. Okay, and the sk here is in fact the step size. Okay? For example, in the Kalman filter, the sk was just the k gain. Okay, so it's exactly the same idea, in fact, which is behind. So in fact, that number sk, you may tweak it a little bit, you may calibrate it, you may do different things to find it. So that number sk is the step size, okay? And it determines how far we move until the in the uphill direction, because we are willing to maximize the m. So we're moving in the direction of delta m. Okay. So that's it for our class today. Okay, we are exactly on time. And I'll stop the recording right now. Thank you all for following. If you have